Good day, folks. I recently saw a video tutorial on the Abacus program, Abacus CAE program, where the YouTuber was explaining the concept behind surface traction available in the Abacus CAE. This particular tutorial is geared to the 3D Experience Release 2025X version, which in it, the Abacus program is buried as the FEA solver. So I want to reproduce the same tutorial, more or less the same tutorial that I saw, but in the context of 3D experience. So when you create your finite element model in 3D experience, quote unquote abacus, uh, as far as there is a toolbar which indicates these three possibilities. One of them is called surface traction. This is the one that I'm going to be dealing with today. And then there's also one with beam load and shell edge load. Now, what I'm going to do is this particular one, which is shown on the right-hand side in the enlarged view. There is an explanation of when this kind of thing is useful, but I want to point out that this is really a more mature version of pressure loading or traction loading. Let's put it that way. Because after all, pressure is a surface traction which is applied in the direction normal to the surface. The particular video that I was talking about was right here. This is the link to it, but it was done for the Abacus CAE interface, which is completely different day and night. So when you click on the surface traction, a dialog box like this opens up, and you can select as the support a face, can be flat or can be curved, and then you can specify a direction and a direction along which, for example, pressure, traction is specified. Now, I will not do an example like that, but I will do a more simplified version, as you'll see in a minute. But there are other options that you've got here. You can select your coordinate system. You can say whether that pressure loading is follower or not, etc. But those are more advanced things that I'm not going to be discussing. The, the, the help for the traction, surface traction is right there in the 3D experience, but it doesn't say very much. So the example that I'm going to do is a clamped beam. I'm not going to model it with beam element. It'll be modeled with solid elements. But the clamped beam, as you see here, the left side is clamped. And on the right side, I will apply a surface traction of 200 psi in the downward direction. So essentially, we have a cantilever beam which is point loaded at the right side, and the value of that point load or that force is the actually shear traction, the traction, surface traction value 200 times the cross-sectional area of that square or rectangle on the side. I'm going to take L to be length to be 15 and the width to be 0.5. These are all in inches. Height to be 1, and I'll use the default or properties of steel, 29 million psi. 29 million psi, and Poisson ratio 0.3. Now, the reason I mentioned this thing about point load and things like that is that I'm going to calculate the finite element results with the elementary strength of material formula, which gives you the tip deflection, if actually I applied a force load, a point force here. Now, the value of that force is going to be traction times area, and the rest of it is just plug in, and I should be 0.0931 inch deflection, maximum deflection. That's the reason that I brought up this thing, because I want to be able to compare my results with something. So let's go ahead to 3D experience on that. Part design on that vertical plane. I will draw my cross section, which is 0.5 by 1, and then I pad it. You notice that the CAD model, the CAD workhorse for 3D experience is actually CATIA. You can see that. So this is going to be 0.5 inches. All right. And this side is 1 inch. So this is the cross section. Exit, and I'm going to pad it by 15. There we are. Okay. So as far as model is concerned, we're all done. So now we're going to go to before I do that, let me apply some material here, just a second. And I'll go to Tools. There's a Tools tab. Find the material. I'm going to create a material. Okay, so let's create a material. I call this thing surface traction tutorial. Surface traction tutorial. Okay, so simulation, very good. And we say okay. That's going to get created, and I put my numbers in it. Young's modulus and Poisson ratio. Here, surface traction tutorial. First of all, let me apply this. Right click, apply. I don't need that anymore. I apply to this, and then green check mark. Now, of course, there are no numbers in here. I double click on it to put my Young's modulus and Poisson ratio. So structural, mechanical, abacus multiphysics, elasticity, there. So what do we know? Young's modulus is 29.01 e to the 6. There we are. And Poisson ratio is 0.3. We don't need anything else. Everything is good. All right, so that information is in there. Now we're going to go and mesh this thing. So let me go. There are different ways you can do that. You can, if you want, you can go to, for example, structure model creation. To mesh it, you go to structure model creation, and it's going to be we can do sure empty FEM, and I'm going to mesh it myself. The actual size of the mesh and type of the mesh is not important because that's really not the focus of this tutorial, and it's a very simple problem. So that's good. Now we're going to mesh it. So mesh, there's no mesh created because I just set an empty one. I'm going to do a tetrahedral mesh on that geometry. Yeah, that size is not critical here, so we say okay. Good. And we apply 3D properties. So go under properties, 3D solid section, and select the part. And material is going to be selected, correct material. That's pretty much it. And now we're going to go to, for example, we can go to structural scenario creation. These steps were explained in the many tutorials on FEA that I've developed in the YouTube channel for 3D Experience. So let's see now, we're going to select our finite element model. We're done, almost done. Okay, so good. So let's go ahead and apply a clamp here. So on the procedure, these things out of the way. On the procedure, we're going to do static step. It's all linear, basically. If you want, you can uncheck this, but it really doesn't matter. I'll do a linear analysis, uncheck that nonlinear geometric effect. And then we're going to go, these things out of the way, boundary conditions. So let me move these things out of the way so you can see a boundary condition. I'm going to clamp. Here's the clamp. I'm going to clamp this side. The icon for clamp is actually the graphical designation is this kind of yellowish looking thing. And on this side, I'm going to apply surface traction. So on the load, notice that you go here. This is the thing that appeared in the transparency here, surface structure. You can see that. Now, I'm going to select the surface. There's a surface. Okay. And I'm going to apply it in the downward direction. So global Z direction. So put down minus 200. And then we say, okay, there we are. Very good. That's pretty much it. So we go to simulate. First of all, this model and scenario check. If anything is critical is missing, it's going to tell us. There's nothing missing here. Very simple problem. That's my mesh. Then I'm going to do simulation check. Again, anything critical is going to tell us. Okay, that's fine. I don't think I forgot anything. There was a warning message there. It's fine. It's running. There is a warning message. We can check that, but the load surface traction has a 0 magnitude. Remove the load. Oh, you know what? Well, we'll find out whether it worked or not, because I think there was something that I missed when I plugged it in there. Yeah, just 1 second. I don't like this warning message, but I'm not going to stop it. I'll wait until it finishes. Give it a minute. I want to show you what the message is saying basically. Okay, you see that? Say close this. We haven't run it yet. These are checks. If you go to the load, see that? Double click on it. I think it's right here. Uh, this should have been 200, and this should have been -1. Notice that nothing changed except that let me update and run it. I'm not going to get that message again. And the reason I run into the situation is that I did a tutorial earlier today, which I was using CATIA V5 FEA solver to show you the same feature available there. And there it's not, it's different. So the mistake that I made here is that what I have to do is I put down the direction of the normal direction of the coordinate system where I want to apply this thing in, and the magnitude here. Okay, just going to put this thing and put it in that direction. I'll come back and talk about this in a minute. And now we're going to do a model check one more time. Everything's up to date. We're going to do a simulation check. This time we're not going to get that warning message. See that? If I had actually ran this thing without making this correction, it would give me all 0 stresses and 0 displacements. That thing that is in the dialog box is not very informative. This is why it may be helpful if you go to the help and try to make sense out of it. Help page and try to make sense out of it. Now let's see what this thing is saying. Okay, that's fine. That's fine. It's okay. It's going to work. In a simple problem, we don't have to worry about warning messages like this. All right, we're going to run it, and this thing better bend down. And we're going to check the number for displacement. Now we're running it. this is a coarse mesh, but at the same time, that's a simple problem. I'm using parabolic element. This is the same warning message that we had before, probably. Yeah, that's fine, no problem. This business of surface fraction can be handled in other ways, but anyway, the purpose of this tutorial was to show you that icon which says surface fraction. This is done, and we're going to look at your deflected result. This is the original, and this is the deflected one. And look at the magnitude of deflection, which should be, oh, this is the 1 meter stress. I don't want that. I want displacement. And a millimeter. Oh my God. Okay, so let me go and change my units to for displacement to inches. Let me go here, preferences. Let's find displacement. Displacement. Be somewhere here. Displacement. What is the actual displacement? Right there. I'm going to change that thing to inches, and then say OK. And displacement in inches, 0.06. Now that doesn't look good. It doesn't agree with this number. So maybe some issues involved. So let me go ahead and do the following. I'm going to go to tetrahedron here, right there, and I'm going to use parabolic, quadratic, because this is a coarse mesh, very coarse mesh, and I'm using linear. So let me change that thing to parabolic and run it again. So we're going to run it this time. It's a parabolic element. And remember, a minute ago we had 0.06. It was supposed to be 0.09, roughly 0.0931. Now I'm using parabolic element. And then if necessary, I'm going to go and refine it further because the size of it I didn't like. That's okay. Yeah, it's done. Yeah, right there. 0.093. 0.093. Very good. Now, what I'm going to do is the following. Before I quit here, so I'm going to go to this load right there. Double click on that. All right. So right now, notice it's downward. So let me put for example, not only put this thing down, but also push it in. So in the direction, I think this is direction Y, if I'm not mistaken. I'll put down a 1 and let's see how it looks like. Okay, no, it's not this one. Put down 1 here. So 1 and 1. See that? It's pushing it down by 200 psi and pushing it into the X by now if you want, for example, to push it in by not 200 by 100, let me make this thing 0.5. Okay, you see that? So it's going to be this number times -1 and this number times that, and this is going to go push it down and of course apply pressure on it. So let's run it. This was not needed to do the present tutorial, but I just want to show you what is the role of that XYZ, which is not clearly explained in the dialog box. Maybe if you read it here, you get some idea, but Remember, I put down for Z minus 1, so multiply 200 by minus 1 is 200 psi down, and I multiply 200 by 0.5, that is pressing against it. So notice that this goes down, and of course it's going to get compressed also. That's pretty much it. Good luck.